Hey guys, this is a video dealing with three of the review questions slash plug and chug questions from the back of chapter 3. So these are kind of worked examples from chapter 3, which again was projectile motion. So the first one we're going to look at is this one. It's number 1 from your review questions. So the first should be the very first question in the entire page, and again this is page 40 in your book. And this question says, how does a vector quantity differ from a scalar quantity? And we learned this a while ago, back in my very first video on physics. But the reason it's in chapter 3, the reason I didn't make it in the chapter 3 series was because I felt that knowing vector and scalar was important for chapter 2. So how does a vector quantity differ from a scalar quantity? So we have vector and scalar, and yellow is not a very good color for this, so I'll use orange. Okay, vector. So I remember I made a chart in the video on vector and scalar, so let's just do that again. Vector, scalar. Okay? So I'm sure you guys know this now because you've gone through chapter 3 and you've learned this stuff, but let's just go into it a little bit. Okay, so vector, we remember, has a direction. Okay? That's key. Direction and, I'll give you time to see if you can remember this. Remember, and, that's not a very good and, but and a magnitude, okay? Now, what does that mean? That means, let's say if I have a plane flying over here, okay, and it's flying this way, okay? Now, we could say it's going 200 kilometers per hour, 200 kilometers per hour, but you see, this is just a magnitude. We need to make it a vector quantity. We need a direction. So let's say it's flying 200 kilometers per hour east. Now it is a vector quantity because it does have a direction. That's just a simple definition of a vector. Now we'll move on to scalar. Oops. Now we'll move on to scalar. Now scalar, remember, magnitude only. Okay. So again, if we have a plane flying like this and it's going 300 kilometers per hour, this is just a scalar. So this could be speed and velocity. So let's give some examples. Velocity is a vector, and speed is a scalar. Okay, so that's basic definition for that. Clear the page. And we'll move on to question number 8. That's not question number 8, I'm sorry. Let me go and grab question number 8 real quick. Here we go. And it says, in the absence of air resistance, so no air resistance, remember, nothing affecting it from the air, why does the horizontal component of velocity for a projectile remain constant while the vertical component changes? So this is probably my favorite question in the whole homework because it's really key for all of projectile motion. This is the basis of projectile motion, basically, in terms of how we use it in conceptual physics without air resistance. Okay, this is key. Okay, so in the absence of air resistance, so we're talking free fall. Why does the horizontal component for a projectile remain constant? Now remember, we talked about this. We had the two different. We had the horizontal. We had the ball rolling horizontally. The ball rolling horizontally. This is one ball over, so 1 second, 2 seconds, 3 seconds, and 4 seconds. Now, why are these distance intervals the same? Because it's not accelerating. Let's say it's on a table here, and I rolled it down the table. It has no acceleration, and that is the reason for that is because gravity is not affecting it. If there was air resistance, you could think of kind of a force pushing it back like this. This could be air resistance, AR, and it would decelerate. Each passing second, this interval would get smaller and smaller and smaller. But since there's no air resistance, this is obviously unrealistic. But gravity can't affect this, so gravity is not making it accelerate. So gravity is not changing the distance between each second. Gravity is not changing how fast it changes its velocity. In fact, it's not changing its velocity. This is horizontal. So remember, for the first, why does horizontal component of velocity for projectile remain constant? No gravity. Whoops. Say no gravity is affecting it, or slash no acceleration. No acceleration. Okay. Now we'll move on to the the vertical component, which is actually more important, I think. While the vertical component changes. Now, so let's look at kind of this diagram, but for vertical. So we have a ball, then ball, and then ball gets further away. So 1 second, 2 seconds, 3 seconds. Now, why does this distance interval get bigger and bigger? Because we know that g, which is acceleration due to gravity, acceleration due to gravity equals 9.8 meters per second squared, or 10 if we're gonna, kind of amongst friends here, 10 meters per second squared. You'll probably see 10 meters per second squared more in your class, but it's actually 9.8. So with every passing second, it's accelerating at 10 meters per second squared. So the velocity is going to increase, so the distance between each second is going to increase. That's just how it works. So that's the answer to your question there. I'm sorry if it wasn't super clear, but go back and watch my video on it, because then it will be very clear, because I did explain it pretty well there, if I do say so myself. Okay, sorry about that, my screen got kind of messed up. Now we will move on to the last question of this video, which is question 19, and it's the first one in the plug and chug. And it says, let me snag it from my Microsoft Word here. It says, this one's very easy, probably the easiest one we've done today. Calculate the resultant velocity of an airplane that normally flies at 200 kilometers per hour if it encounters a 50 kilometer tailwind and a 50 kilometer headwind. Okay, so this is very easy. So we have this plane here. Okay, you guys do know how bad my plane drawings are, so don't judge me here. Okay, so let's just call this a plane. Okay, and it's flying at 200 kilometers per hour normally. Now let's remember, what is resultant? The resultant is what you get after you combine two vectors, basically. So we have this, let's say this is northbound, okay? I'm surprised in this question they didn't actually include a direction, so it's a little tricky that they use velocity, because they just use 200 kilometers per hour, so they probably should have put a direction, but they know that we know what vectors are, so they're just using this for simplicity's sake. But let's take the first question. It encounters a 50 kilometer tailwind. So tailwind, pretty intuitive. It means wind's coming from your tail or your back. So here's the wind, 50 kilometers per hour north, because it's coming from our tail. It's coming the same direction as us. So you simply add these together and we get 250 kilometers per hour north. Okay, that's our resultant velocity vector here for the first part of the question. Now, the second part, 50 kilometers headwind. Pretty easy. Okay, 50 kilometers per hour south, because that is the opposing direction of north. And so when it's south, you simply subtract, and we'll get 150 kilometers per hour. Now this is the part you have to be careful about. For the direction, it's obviously 50 is not strong enough to push something moving at 200 kilometers per hour back south. So since the 200 is bigger than the 50, we're just going to say it's still going north, which is true. It's just moving slower. So there we go. And those are some worked examples. I'll see you guys chapter 4.